a signal, not random, a force, not fully understood. Something out there is breaking the rules of physics. And the most unsettling part is this. The people who understand the universe better than anyone else are not excited. They are uneasy. Even leading physicists admit that we might not be ready for what we are starting to uncover. Deep space was once seen as silent and empty, a cold void with distant stars scattered across it. That idea is gone, completely gone. Today, space is loud, it is active, it is unpredictable, and in some cases, it behaves in ways that do not make sense.
Modern telescopes are more powerful than ever.
Instruments orbit Earth. Others sit deep in remote deserts, scanning the sky night after night. They collect massive amounts of data. Every second, signals arrive from billions of light years away. Light, radiation, bursts of energy, patterns begin to form. But instead of clarity, scientists are finding confusion. There are signals that repeat with no clear source, bursts of energy that appear and vanish in milliseconds, regions of space that bend light in ways that should not happen, objects that seem to defy the limits set by known physics.
These are not small errors.
These are not simple gaps in measurement. These are real observations confirmed again and again. Here is something most people do not know. The part of the universe we can actually see is incredibly small. Everything you know, every star, every galaxy, every planet makes up less than 5% of reality. The rest is hidden, dark matter, dark energy, unknown forces. Scientists can measure their effects, but they cannot directly observe them. It is like watching shadows move without ever seeing what is cast in them. This means one thing: we are not studying the universe. We are studying a tiny fraction of it. And even within that small fraction, we are already finding things we cannot explain. Some of the most disturbing discoveries come from signals that travel across unimaginable distances. They carry enormous amounts of energy, more than entire galaxies can produce in a short moment. These signals appear suddenly, then they vanish. Some repeat, some do not. Scientists can detect them clearly, but their origin remains a mystery. Not a simple mystery, a deep one that challenges existing theories. Then there are black holes, regions where gravity becomes so strong that nothing can escape, not even light. For years, they were considered cosmic endpoints. Now they are something far more complex. They store information. They distort space and time. And at their core, the laws of physics begin to break down. Not bend, break. This is where fear begins to enter the conversation. Not fear of creatures, not fear of invasion, but fear of ignorance. The realization that the universe might operate on rules we do not yet understand. Greene has spent years explaining the deepest ideas in physics. He speaks about space, time, and reality itself. And even he acknowledges something unsettling. Our current theories might be incomplete. They might be fragments of a much larger truth, a truth that remains hidden. There is a gap between what we observe and what we can explain. That gap is growing. Every new discovery seems to widen it. Scientists expected that better technology would bring answers. Instead, it is revealing deeper questions. Another lesser-known fact is this: the universe is not just expanding, it is accelerating. Something is pushing galaxies apart faster and faster. This force is invisible. It cannot be directly measured, yet it dominates the entire cosmos. No one knows exactly what it is. It does not fit neatly into existing theories. Think about that for a moment. The largest force shaping the universe is something we cannot fully understand. At the same time, quantum physics reveals strange behavior at the smallest scales. Particles can exist in multiple states at once. They can influence each other instantly across vast distances. These effects are real. They have been tested and confirmed, but they do not align with how we understand space and time on a larger scale. So now there are two sets of rules, one for the very large, one for the very small. and they do not match. Scientists have been trying to unify them for decades.
So far, no complete solution exists.
This creates a deeper question. If the rules we rely on are incomplete, then what else are we missing? What else is happening in deep space that we simply cannot interpret yet? There is also the issue of observation limits. Light travels at a finite speed. That means when we look into space, we are looking into the past. The farther we look, the older the light becomes. Eventually, there is a boundary, a point beyond which we cannot see. Not because nothing exists there, but because its light has not reached us yet. Beyond that boundary could be anything. Different structures, different laws, entire regions of reality that operate in ways we cannot even imagine with current knowledge. This is where the idea becomes unsettling. Not because something is clearly visible, but because something might be there that we cannot yet detect properly. Something that influences the universe in subtle ways. Something that leaves traces but never fully reveals itself. Scientists are careful with their words. They rely on data. They avoid speculation without evidence. But even within those limits, there is a growing acknowledgement that we are missing something fundamental. The deeper we look, the more the universe resists simple explanation. In this video, you will discover the signals that defy explanation, the hidden forces shaping everything around us, the limits of our current understanding, and the reason why some of the brightest minds in physics are beginning to question how much we truly know. This is not about science fiction. This is about real data, real observations, and real uncertainty. Because the truth is simple. The universe is not just stranger than we thought. It might be stranger than we are capable of understanding. And that is where the real fear begins. Welcome to the channel. If you want to explore the deepest mysteries of space and uncover the truth behind what science is still trying to understand, make sure to subscribe. Space looks empty, silent, still. That is the illusion. Every direction you look, every dark gap between stars feels like nothing is there. But that is only because the human eye sees almost nothing of what actually exists. The truth is far more unsettling. Space is not empty at all. It is full, packed with things we cannot see, cannot touch, and barely understand. The stars, planets, and galaxies that light up the night sky feel vast. They feel like everything, but they are only a tiny fraction of reality, less than 5%. That is all the normal matter in the universe. Everything else is hidden. Scientists call it dark matter and dark energy. Names that. Sounds simple, but they hide a deeper problem. These are not just unknown substances. They are unknown behaviors, unknown rules, unknown forces shaping the entire cosmos. Dark matter does not emit light. It does not reflect light. It does not interact with normal matter in any direct way that we can detect. Yet it is everywhere. It surrounds galaxies like an invisible skeleton. Without it, galaxies would fall apart. Stars would drift away into the void. The structure of the universe itself would collapse. Here is what makes it more disturbing. Scientists know it is there because of gravity. They see how galaxies rotate. They measure how light bends around invisible mass. The numbers do not match unless something unseen is holding everything together. Something massive, something dominant. And still, no one has directly observed it. Then there is dark energy, even stranger, even more mysterious. It is not pulling things together. It is pushing them apart. The universe is expanding faster and faster. Galaxies are drifting away from each other at increasing speed. This acceleration should not happen under normal physics. Gravity should slow it down. But something is overpowering gravity on the largest scale. That something is dark energy. It makes up nearly 70% of the universe, the single largest component of reality. And scientists still do not know what it actually is. Think about that. The majority of the universe is controlled by a force we cannot explain. But the strangeness does not stop there. Even the so-called empty vacuum of space is not truly empty. At the smallest scales, space is alive with activity. Quantum fluctuations constantly create and destroy particles. Tiny bursts of energy appear and vanish in fractions of a second. This process never stops. It happens everywhere all the time. This means that even in the darkest, coldest regions of space, there is movement, there is energy. There is something happening beneath the surface of what looks like nothing. Scientists once believed that empty space was a passive stage where the universe played out. That idea is gone. Now, space itself is part of the system. It has structure. It has energy. It might even hold information we cannot yet access. And this creates a deeper problem. If 95% of the universe is invisible and behaves in ways we do not understand, then every observation we make is incomplete. Every theory is built on missing pieces. Every model of reality could be fundamentally flawed. This is not a small gap in knowledge. This is a massive blind spot. The universe is not just hiding secrets. It is built on them. And as scientists push deeper into space, they are not finding empty silence. They are finding something far more complex waiting beneath it. Black holes were once seen as simple endings. Points in space where everything falls in and nothing comes out. That idea felt clean, final, easy to accept. That idea is wrong. Black holes do not just destroy, they hide, they erase information from the visible universe in a way that still does not make sense. And this is where the real fear begins. At the edge of a black hole is a boundary called the event horizon. Once anything crosses that line, it is gone forever. Light cannot escape. Signals cannot return. No message can tell us what happens next. It is the ultimate wall in physics. But here is the problem. According to the laws of physics, information should never be destroyed. Not truly. Every particle carries information about its state, its position, its energy, its history. Even if something changes form, that information should still exist somewhere. Black holes seem to break that rule. When something falls in, all of its information appears to vanish. Not hidden, not transformed, just gone. This creates a paradox that has troubled scientists for decades. If information can be destroyed, then the foundation of physics begins to crack. Some theories suggest that the information is not lost. It is stored on the surface of the event horizon itself, encoded in ways that are almost impossible to decode. Others suggest that it slowly leaks back out through a process known as Hawking radiation, a faint glow emitted by black holes over time. But there is a catch. That radiation appears random. It does not clearly carry the detailed information of what fell in. It looks like noise, not a message. This leaves a disturbing possibility. Either information is truly lost or our understanding of physics is incomplete. Inside the black hole, things become even more extreme. Gravity grows infinitely strong. Space and time begin to twist in ways that defy logic. At the center lies a singularity, a point where density becomes infinite and the known laws of physics stop working. Not bend, not stretch, stop. Equations break down, predictions fail, science reaches a limit. This is not just a gap in knowledge, it is a wall. Some physicists believe that beyond this point, a deeper layer of reality exists, a set of rules that we have not yet discovered, a framework that could unify gravity and quantum mechanics. But until that is found, the interior of a black hole remains unknown. And then there are the more unsettling ideas. Some theories suggest that black holes are not endpoints at all. They could be gateways, bridges connecting distant parts of the universe, or even entirely different universes. These theoretical structures are called wormholes, solutions to the equations of gravity that allow space to fold in on itself. There is no direct evidence that they exist, but the math allows for them. If that is true, then falling into a black hole might not mean destruction. It might mean transition, movement to somewhere else, somewhere unreachable by normal space. Other ideas go even further. Some suggest that entire universes could exist inside black holes, that each one could be a seed for a new cosmos, hidden from the outside forever. These ideas are not proven, but they are taken seriously enough to be studied, and that is what makes black holes so unsettling. They sit at the edge of knowledge. They expose the limits of everything we think we understand. They force scientists to confront the possibility that the rules of reality are not complete. Because if physics breaks down inside a black hole, then the universe is hiding something far deeper than darkness.
A signal appears. Then it is gone.
It lasts less than a second. Yet, in that brief moment, it releases more energy than the sun produces in days, sometimes even more. It travels across billions of light years, passes through galaxies, dust, and radiation, and still arrives strong enough to be detected on Earth. These are called fast radio bursts, FRBs. They were first discovered by accident, hidden inside old telescope data. A single spike, easy to dismiss as noise, but then it happened again and again. Different locations, different times, always the same pattern. A sudden flash of radio energy, then silence. At first, scientists thought these signals must be one-time events, catastrophic explosions, colliding stars. The final moments of something massive. That explanation made sense until it stopped making sense. Some FRBs repeat. That changes everything. A repeating signal means the source survives. It sends out bursts, pauses, and then sends more. Not once, not randomly. In some cases, the timing shows structure. Not perfectly regular, but not completely chaotic either. One source sends bursts in a cycle, active for a few days, silent for weeks, then active again. Another produces clusters of signals with gaps in between, almost like a pattern trying to form. This is where things become unsettling, because nature can create randomness. Nature can create explosions, but patterns suggest something else, something controlled, or something governed by rules we do not yet understand. The energy involved is extreme. To produce a single FRB, the source must release an enormous amount of power in a very short time. Some estimates suggest that the energy equals what the sun emits over several days, compressed into milliseconds. No human technology comes close, not even in theory. Scientists have proposed explanations. One leading idea involves magnetars. These are neutron stars with incredibly strong magnetic fields. When their magnetic energy shifts or cracks the surface, it can release powerful bursts.
This matches some observations, but not all.
Some FRBs originate from regions where magnetars are unlikely to exist. Others show properties that do not fit the model cleanly. The signals pass through dense environments, leaving traces in their structure. Twists, delays, polarization patterns that suggest complex interactions with matter and fields along the way. Each new detection adds more data, but it does not simplify the mystery. It deepens it. Another lesser-known detail is how precise these signals are. The dispersion of the signal, how different frequencies arrive at slightly different times, allows scientists to measure the distance it traveled. This confirms that many FRBs come from far outside our galaxy, some from billions of light years away. This means the source is not just powerful, it is also ancient. The signal began its journey long before human civilization existed. And yet it arrives now, detected by instruments that only recently became sensitive enough to notice it. There is also the question of why we are seeing more of them now. New telescopes are designed to scan large areas of the sky continuously. They are catching events that older systems would miss. This suggests that FRBs might not be rare at all. They might be happening constantly across the universe. We just did not see them before. That raises another possibility. The universe may be filled with signals we have not yet learned how to detect. Patterns hidden in noise, messages buried in data that we do not fully understand. How to read. Some scientists remain cautious. They focus on natural explanations, extreme astrophysical events, exotic stars, unusual environments. But even within those explanations, there are gaps, missing pieces, behaviors that do not fully align with theory. And that is where the tension builds. Because every time a new signal is detected, it brings more questions than answers. There is a boundary in the universe, not a wall, not a barrier you can touch, but a limit that cannot be crossed by observation. It is called the observable universe. Everything humans have ever seen, every galaxy mapped, every signal detected exists inside this boundary. Beyond it, there is more space, more matter, more reality, but it is hidden, completely unreachable by light. This happens because light takes time to travel. When you look into space, you are not seeing objects as they are now. You are seeing them as they were in the past. A star 1,000 light years away appears as it was 1,000 years ago. A galaxy millions of light years away shows a version of itself from millions of years in the past. Now extend that idea to the entire universe. There are regions so far away that their light has not had enough time to reach Earth since the beginning of the universe. Not because they are too dim, not because they are blocked, but because the universe itself has not existed long enough for their light to arrive. This creates a horizon, a limit to visibility. Beyond that horizon, there could be countless galaxies, entire structures, unknown phenomena. But no signal from them has ever reached us, and maybe never will. Here is where it becomes more unsettling. The universe is expanding. Space itself is stretching. This means distant galaxies are moving away from us. The farther they are, the faster they move. At extreme distances, this expansion becomes so strong that it pushes regions of space away faster than light can travel. That means some parts of the universe becoming permanently invisible. Even if they once emitted light toward us, that light will never arrive. It is being stretched and carried away by the expansion of space itself. So the observable universe is not just limited, it is shrinking in terms of accessible information. There are parts of reality that are already lost to us. Another lesser known detail is this. The conditions near the edge of the observable universe are very different from what we see nearby. The earliest light we can detect comes from a time when the universe was extremely hot and dense, a faint glow known as the cosmic microwave background. It is a snapshot of the universe when it was only about 380,000 years old. Beyond that point, everything becomes opaque. Light could not travel freely yet. The universe was filled with charged particles that scattered radiation in every direction. This creates a second boundary, a deeper one. So even within the observable universe, there is a layer we cannot see beyond using light. This means our view of reality is limited in two ways, distance and time, and that raises a deeper question. If we cannot observe beyond these limits, how can we be sure that the laws of physics remain the same everywhere? The rules we understand are based on what we can measure, but we are measuring a small region of a much larger system. There could be variations, subtle or extreme, regions where constants behave differently, where forces interact in ways that do not match our models. Some theories even suggest that the universe might be one of many, a multiverse, each with its own set of rules, its own structure, its own version of reality. There is no direct evidence for this, but the mathematics behind some models allows for it. And that leaves a gap, a quiet uncertainty. Because if the observable universe is only a small window, then everything outside that window remains unknown, not just unseen, unknowable, at least for now. And somewhere beyond that edge, reality may not look anything like what we expect. Physics is supposed to explain everything, from falling objects on Earth to the motion of galaxies across billions of light years. But the deeper scientists look, the more they find cracks in the structure. Two of the most successful theories in history stand at the center of modern science. One describes the very large, The other describes the very small. General relativity explains gravity, stars, and space itself. Quantum mechanics explains particles, atoms, and energy at the smallest scales. Both work perfectly in their own domains, but they do not agree. When these two frameworks are pushed together, they stop matching. The equations break down. Predictions become inconsistent. This is not a small technical issue. It is a fundamental conflict in how reality is described. For example, relativity treats space and time as smooth and continuous, a fabric that bends and curves. Quantum physics treats reality as discrete, probabilistic, and uncertain at its core. Particles do not have fixed positions until they are measured. Events do not follow strict paths. Both ideas are supported by experiments. Both are accurate, yet both cannot be fully correct at the same time. This is where the tension begins. Scientists have been trying to merge these two frameworks for decades. They search for something deeper, a hidden structure that can explain both gravity and quantum behavior in a single system, a theory of everything, something that sits beneath the layers we already understand. String theory is one attempt. Loop quantum gravity is another. These ideas suggest that space itself might not be continuous. It might be built from smaller units like pixels in a digital image, or that particles are not points but vibrating strings of energy in higher dimensions. But none of these theories have been confirmed. Experiments have not yet reached the energy levels needed to test them directly. So they remain mathematical possibilities, elegant, powerful,
but unproven.
There is also a lesser-known issue. Some of the biggest puzzles in physics are not about what we see, but about what we measure indirectly. The expansion of the universe, the behavior of dark matter, the acceleration driven by dark energy. All of these fit into models only by adding unknown components. It feels like building a structure and constantly needing invisible support beams to keep it standing. This leads to a growing concern. The current models might not be the final description of reality. They might be approximations. Very accurate ones, but still incomplete. Like zooming into a map that becomes more detailed but never fully reveals the territory itself. And here is where the fear enters. It is not fear of collapse or danger. It is something quieter, a realization that the foundation of modern physics might be partial, that the rules used to describe everything might be missing a deeper layer. Some physicists describe it as standing at the edge of understanding, looking at equations that work, but knowing they cannot be the whole story, because every time new data arrives from space or particle experiments, it adds precision but also complexity. New anomalies appear, small inconsistencies that do not fit existing models. And instead of disappearing with better measurements, they persist. This suggests something important. Nature is not wrong. The models are, which means there is still something fundamental waiting to be discovered. A framework that could change how space, time, and matter are understood at the deepest level. And until that framework is found, physics remains unfinished. Telescopes are becoming more powerful every year. Satellites scan deeper into space. Sensors pick up signals that were once invisible. Data is arriving faster than ever before. But understanding is not keeping up. There is a growing gap between what we can detect and what we can explain. We are collecting more information about the universe than at any point in human history. Yet large parts of that information do not make sense within current scientific models. This creates a strange situation. Science is no longer limited by lack of data. It is limited by interpretation. Signals are being recorded that scientists cannot fully classify. Energy patterns appear that do not match known sources. Light behaves in ways that challenge established equations. These are not rare events anymore. They are becoming more common as detection systems improve. One lesser-known fact is that many discoveries in astronomy were first dismissed as instrument errors. Fast radio bursts, unusual pulsars, and even early gamma ray detections were once considered noise. Only after repeated observation did they become accepted as real phenomena. This pattern suggests something important. The universe may be revealing itself faster than human models can adapt. There is also the issue of scale. Modern instruments are so sensitive that they pick up extremely faint signals from deep space. But sensitivity alone does not guarantee understanding. A signal can be detected without knowing what produced it. This leads to a serious possibility. Some of what is being observed may be misunderstood at a fundamental level, not because the data is wrong, but because the framework used to interpret it is incomplete. In science, interpretation depends on existing knowledge. When something new appears, it is compared against known categories: stars, black holes, galaxies, radiation sources. But if a phenomenon does not fit any category, it becomes uncertain. It may be labeled as noise, anomaly, or unexplained. Only later, after more data is collected, does its true nature begin to emerge. This delay between detection and understanding creates a blind spot. Another factor is the sheer volume of data. Observatories generate massive streams of information every second. No human team can analyze it all manually. Artificial systems help, but even they rely on patterns learned from existing knowledge. If something is truly new, it may not be recognized correctly at first. This raises a deeper concern. Humanity may be observing the universe through tools that are already slightly outdated in terms of understanding. Not because the tools are weak, but because the interpretation layer has not caught up with the speed of discovery. There are also theoretical possibilities that add to the uncertainty. Some physicists suggest that unknown forces or fields could be interacting with matter in subtle ways. Effects that are too small to notice individually but significant when viewed on cosmic scales. If that is true, then current models may only capture part of the picture. There is also the question of bias in interpretation. Scientists naturally try to explain new data using familiar frameworks. This is how progress usually happens. But it also means that truly unfamiliar phenomena may be forced into existing categories, even if they do not fully belong there. And that is where the tension builds. Because the universe does not adapt to human understanding. Human understanding must adapt to the universe. Right now, there are signals, forces, and behaviors being recorded that sit at the edge of explanation. They are real, measurable, persistent, but not fully understood. And as technology continues to advance, more of these unknowns are emerging faster than they can be decoded. The deeper the universe is studied, the less simple it becomes. Every answer leads to another question. Every discovery reveals something unexpected behind it. Space does not settle into clarity. It expands the mystery. The more advanced the tools become, the more complex reality appears. What was once thought to be empty space is filled with invisible matter and energy. What was once thought to be stable physics begins to break at extreme scales. Signals arrive from deep space that no theory fully explains. Black holes hide information in ways that challenge the foundations of science. Even the edge of the observable universe limits what can ever be known. Piece by piece, the idea of a fully understood universe becomes harder to hold. Science continues to move forward. It measures more. It detects more. It reaches farther than ever before. But understanding does not always grow at the same speed. Sometimes it lags behind. Sometimes it struggles to keep up with what is already being seen. This is where the real shift begins. The universe may not be a simple puzzle waiting for a final answer. It may be something far more complex, something that does not fully fit within human frameworks of logic and measurement. A system where each layer reveals another layer beneath it. And at the center of all of this sits one uncomfortable idea: the possibility that reality itself is deeper than human understanding can currently reach. Not just unknown, possibly unknowable, at least in full. This does not mean science is failing. It means science is doing exactly what it has always done: pushing into the unknown, testing the limits. finding the edges of what can be understood. But now, those edges seem further away than ever before. Even leading physicists like Greene have pointed toward this reality, that the universe may be governed by principles we have not yet discovered, principles that could completely change how space, time, and existence itself are understood. So the question is no longer only about what is out there in space. It is also about how much of it can ever be fully known. Because every step forward seems to reveal something larger waiting behind it, a structure beneath the structure, a rule behind the rule, a deeper level of reality that remains just out of reach. And as the search continues, one thought remains. The real mystery may not be the universe itself. It may be how limited the understanding of it still is. If this journey into deep space and hidden physics sparked your curiosity, take a moment to like the video and subscribe to the channel. There is much more to explore and even more waiting to be uncovered.